So now we're at the point where we're going to see how much energy can be generated by these electrochemical cells. On the back of your notes, there's a paper that you can rip off, which is called it's a table of standard reduction potentials. So if you go all the way to the back of this packet, you'll see something that looks like this. Okay, please note, just like when we had like STP for gases, these reduction potentials are only true at standard conditions, which is a temperature of 25 degrees Celsius and 1 molar. Do you need to remember that? No, not like you need to remember STP. But we will talk about non-standard conditions later. Okay, so, to determine the energy produced by a battery or electrochemical cell is measured in volts. Okay, and when you're trying to get these energies, okay, or you're trying to calculate the E naught for a cell, okay, in order for the cell to work, okay, the E naught needs to be positive. Okay, if the E naught is positive, okay, the cell will generate energy, and it can occur without inputting energy. You're going to see the second half of this unit. We're going to deal with sort of redox reactions where you need to input energy to make the reaction occur. Okay. Now there's this formula which is used to calculate the E cell. Okay, which I don't like. Okay, because you're going to see in a second. All right. So it's the energy of the reaction that's occurring at the cathode minus the energy that's occurring energy of the reaction that's occurring at the anode. I don't like that equation. To me, it's confusing. If we take a look at this table, okay, this table is the energy for the reduction to occur. So, like, for example, if we look here, we look at copper. So, where's copper solid? So here, this is the one that we did in the just now. Okay, when copper 2 gains electrons, okay, 0.34 volts of energy is generated. Okay. And then we have zinc, which is what we also use. Where are you, zinc? Here. But this is the reduction. Okay, this here is the reduction reaction. So if we want to find out the energy of the oxidation reaction, okay, we have to reverse the sign. So to get the energy, okay, of the cell, you take the energy of the reduction, which remember is occurring at the cathode, and you keep the sign that it is. And then you find the reaction that's occurring at the anode, okay, and you subtract it. Or just make the sign negative. Okay, this will make more sense, okay, when we do an example. So we're going to do an example now. You should leave this table out. No, wrong thing. Okay, so here we have a galvanic cell that's going to be based off of this reaction. And the first thing it says, we're going to determine what is oxidized and what is reduced. Okay, so here, aluminum is going from +3 to 0, right? So aluminum was reduced, and magnesium is going from 0 to +2, so magnesium was oxidized. Okay, I'm going to write the balanced half reactions here. Okay, so we have magnesium solid. Again, I'm doing the oxidation first, it doesn't matter. Going to magnesium +2. And we're going to generate 2 electrons, or lose 2 electrons. And those electrons are going to travel to the aluminum ion and become aluminum solid. And in order to do this, from +3 to 0, we have to have 3 electrons. Now you'll notice again that these reactions are not balanced, so we have to multiply them to make the electrons equal. So we need to multiply this reaction by 3, so 3, and this becomes 6. And then we need to multiply this reaction by 2. So 6, 2, and 2. So now we have our balanced half reactions. Again, this is the oxidation, and this is the reduction. Okay. Now, we're going to calculate the E naught. And again, this is the oxidation. So this is occurring at the anode. Okay. And this is the reduction. So this is occurring at the cathode. And in class on Monday, we're going to have a lot of practice with this. So now we need to calculate the E naught. So we need to go to the table. Now I'm going to bring the table. And I'm going to find the E naught for this oxidation reaction. I'm going to find magnesium solid somewhere on this table. Okay, we need to bring up the... So where is my magnesium solid? I'm looking for the reaction. So it's right here. Magnesium solid. Right here. This one right here. Okay, so now, this is showing the reduction. Okay, notice the negative 2.37. Okay? But when we have it in our thing, or in our problem, this is the reduction reaction, we have it as an oxidation, right? Because the reaction is flipped. So what we have to do is we have to reverse the sign of that. Okay? Now we're going to try to find this reaction on the paper. And was aluminum, so we have it here, right here. And again, this is the reduction, right? We're starting at +3, and on our paper we also had +3. So, and it's negative 1.66. So we go back, and we're going to write that in there. You don't have to reverse the sign because it's already in the reduction form. And then all you have to do to find the energy of the reaction is to add those two energies. We do that, and we get 0.17. And remember, this is measured in volts. I mean, 0.71. Sorry, 0.71. Okay, now, notice that we do not multiply these energies by the factors in here. They're not multiplicative. You just get them directly from the table. You should never multiply a value from the energies, the reduction potential table. On the AP exam, you're not going to get that table. They will give you it in the problem if they need it. Okay, but you do not multiply by coefficients when you're getting these voltages. Okay, now there's one more type of problem that they could give you. Okay, and so here we want to build a galvanic cell. This is what you're going to sort of do in class in more detail with the pictures and modeling and stuff like that on Monday. Okay, based on the following half reactions. Notice that these are both reductions, okay, because the energy of the electrons are being gained. Okay, now the question is, we're going to remember when we do a galvanic cell, one of the metals needs to be oxidized, okay, and in order for the galvanic cell to work, the E0 needs to be positive, okay. So which one of these, okay, reactions should we reverse to make an oxidation? Remember, when the oxidation is going to occur at the anode, okay, to make the E0 positive. Remember, we add them, okay. Well, if we make this one positive, right, and we add it together, the E0 is still going to be negative. Like if this one's positive, okay, the E0 is still going to be negative, okay. So this one won't work, okay. But if we make this one positive, okay, and we add them two together, then the overall E0, okay, will be positive. If I add it together, it doesn't really matter, but I'll do it. So 1.18 minus 0.44, and we'll get 0.74 volts, and now the energy is positive, and that electrochemical cell will work. Okay. But what that means is that we have to flip this reaction. In order to flip the sign, right now it's a reduction, we need to flip this sign. So now the solid is first, okay, and we're taking the electrons from it. And this again, and plus 2 electrons. This reaction, okay, would occur at the anode, okay, so we're flipping it, so this would occur at the anode, and the reduction would occur at the cathode, okay. The other way wouldn't work. Okay. Monday in class, you're going to be building these cells with a model, okay, and working sort of with the E0s, okay. But you can answer the guided questions, and I'll see you on Monday.